In this video, we are going to explore NumPy, one of the most popular Python libraries for data manipulation, especially when dealing with large datasets. According to Wikipedia, NumPy supports large multi-dimensional arrays and matrices, along with a collection of high-level mathematical functions to operate on them. Before we can use NumPy, we need to import it. We do this by using the command import numpy snp. The snp part is a common convention that allows us to use a shorthand when calling NumPy functions, making the code easier to read and write. Let's start by looking at how to convert a Python list into a NumPy array. In this example, we create a simple list with the values 1, 2, and 3. Using the type function, we can see that this is a standard Python list. To convert it into a NumPy array, we use the np.array function, passing the list as an argument. After conversion, the list becomes a NumPy array. If we want to keep it as an array for later use, we assign it to a new variable, such as myr. Using type again on this new variable, we see that this is now a NumPy ND array, which is the object type for NumPy arrays. Now let's look at creating a two-dimensional array. We start with a nested list, like 1, 2, 3 for the first part, and 4, 5, 6 for the next, and then 7, 8, 9. This list contains 3 smaller lists, each representing a row of data. To convert it into a NumPy 2D array, we again use the np.array function. Once converted, the result is a matrix, also known as a 2D array. You can think of this as a grid with rows and columns. To check the dimensions of this matrix, we use the .shape attribute, which tells us the number of rows and columns. In this case, the shape is 3 by 3, meaning 3 rows and 3 columns. NumPy provides a number of built-in methods to make working with arrays easier. Let's go over a few of them. First, the np-arrange method. This creates an array of numbers between a start and a stop value with an optional step. For example, calling np-arrange with the values 0, 11, and 2 will generate an array starting from 0, ending just before 11, and stepping by 2, giving us the values 0, 2, 4, 6, 8, and 10. Next is np.ones. This method generates an array filled entirely with ones. By default, the elements are floats. If we pass a single integer as an argument, like np.ones 5, it creates a 1D array with 5 ones. Alternatively, we can pass a tuple to specify the shape, such as np.ones with a shape of 3 and 5, which creates a 2D array with 3 rows and 5 columns, all filled with ones. Similarly, there's np.zeros, which works exactly the same as np.ones, except it fills the array with zeros instead of ones. As there are cases where we might need a different value than a 0 or a 1, we can simply broadcast operations to every element in an array. For example, if we need a matrix with 4 rows and 6 columns, with 7s at each position, we can use np.ones, provide the shape with 4 rows and 6 columns, and after that, we simply add 6 to all of those elements, resulting in a matrix of 7s. Or if we need an array that contains 10 times the number 100, we simply set up 10 times the number 1 with np.ones and multiply this array with 100. You see that np.zeros and np.ones can serve to set up large arrays without us having to set them up manually. And those methods are not the only ones to set up matrices. We also have np.linspace. It creates an array with linearly spaced numbers. It needs a start value, a stop value, and the number of values that should be linearly spaced between the start and stop value. In contrast to np.arrange, it can also generate floating point values, and its start and stop values are both inclusive. With np.arrange, np.zeros, .ones, and .linspace, we saw several methods to set up matrices with fixed values or value intervals. But NumPy also has built-in random number generation. The method np.random.rand creates an array of random numbers between 0 and 1, drawn from a uniform distribution. For example, np.random.rand of 3 generates 3 random values between 0 and 1. You can also create multi-dimensional arrays by passing more arguments, like np.random.randn of 5 by 5. Another useful method is np.random.randn, which generates random numbers from a normal distribution with a mean of 0 and a standard deviation of 1. You can specify how many numbers you need, and like before, you can also create multi-dimensional arrays. For random integers, NumPy provides np.random.randint. This method generates random integers between a low value, which is inclusive, and a high value, which is exclusive. You can also specify how many integers you want. For instance, np.random.randint of 1, then 110 will generate 10 random integers between 1 and 99. Reshaping arrays is another powerful feature in NumPy. Suppose we have a one-dimensional array with 25 elements. We can reshape it into a matrix using the reshape method, as long as the total number of elements matches the new shape. For example, we take the array, saying .reshape on that, and providing 5 by 5, which will reshape this one-dimensional array into a 5 by 5 matrix. It is important to ensure that the new shape is compatible with the number of elements. For example, if the array has 25 elements, you cannot reshape it into a 3 by 5 matrix, as this would only hold 15 and not 25 elements. Finding the minimum and maximum values in an array is straightforward in NumPy. The np.min and np.max methods return the smallest and the largest values in the array respectively. Let me create an array with some random integers between 0 and 50. Then we can use np.min on our array to find the smallest number, and np.max to find the largest. If you need to know the position of these values within the array, NumPy also provides np.argmin and np.argmax, which return the index of the minimum and the maximum values. Later in the deep learning part, the array's data type might be important. To get the array's data type, you simply get the array variable and say .dtype on that. In this case, the array is of data type integer with 32 bits. NumPy arrays, like Python lists, allow you to select individual elements and slice ranges of elements. You might remember that the selection of an individual element is called indexing. And indexing NumPy arrays is the same as indexing a Python list. I will create a new and smaller example array for this with np range between 0 and 11 to get values from 0 to 10. Remember that indexing also starts at 0, So if I get this array and provide the index 4, I receive the element at the 5th position. When we try to receive several elements from an array, we are talking about slicing. In one-dimensional arrays, slicing is done by specifying a range of indices, such as selecting all elements from index 2 to 6, or selecting all elements up to a certain index. We can do that with using a colon in front of the index. The named index will not be included. So we would select the indices 0, 1, 2, 3, and 4 in this case. If we set the colon after the index, we select all elements from this index onwards. In this case, the index is included in the selection. Let me quickly copy an example for a two-dimensional array. We see that its shape now has two dimensions, or axes as they are also called. In such a two-dimensional array, you can also refer to those dimensions as columns and rows. To select a single element from such an array, we again start with providing a first index in square brackets. As you can see, this results in a selection of a whole row, and as I provided the index 1, I select the array's second row. Now to select a single value, I need to make my selection more precise, which I can do with another selection. The first one returns a whole row of elements, and the next one selects the element at index 1 from this row. As having several brackets behind each other reduces the code's readability, we can make the selection more efficient and put everything into a single bracket and separate the selection of the row and the column by a comma. Slicing a two-dimensional array is very similar to slicing a one-dimensional array. With the first position, we will again select the rows. If I set a colon 2, I will receive the first two rows of data. If I then extend this selection with the selection of the columns, for example by selecting all columns from index 1 onwards, I receive a slice of the data. As you can see, the colon symbol is very important for slicing. But especially for more dimensional arrays, the colon symbol is very important, as they can be used to keep specific data in a selection. Writing a selection with just a colon for the row selection, I can select all rows from the input array. Then I can, for example, select the column index 0 from the data and receive only the first element in each row. You can also apply a specific condition as a selection method. A simple condition could be a comparison against a threshold. If the element is larger than 6, we want to keep it. This only returns the elements that meet the condition. When working with arrays, it's important to understand how copying works. I would like to show you a little example. I set up an array with values from 0 to 10 with NP range. Then I create a subset of this array by selecting the first 5 elements and saving the selection in a new variable. It looks like the new array is an independent variable that just holds a subset of the data. And I want to change all of those 5 values to minus 999. For now, it looks like I have changed the 5 values of my new array to minus 999. But if I check the original array, the first 5 elements have been changed as well. This happens because even if I created a new variable for the subset was still pointing at its original array. To prevent this, we can make a copy of an array. This way, the original array remains unchanged and you can modify the new array independently. After we have already talked about two-dimensional arrays and I've already mentioned their different axes, we need to talk about that those axes can be used within calculations. First, I set up a fresh array, which I reshape to a matrix of 4 rows by 5 columns. NumPy has got a lot of inbuilt methods to do all kinds of calculations with arrays, like taking the mean with np.mean, or the median, or the sum. However, in all those cases, we receive the result considering all elements at once. But what if we want to have the sum for each row or each column? Then we can specify the axis along which the calculation should happen. If we want to get the sum per column, we specify axis 0. Axis 0 is the rows in this case. So this expression means that the rows will be collapsed and the calculation will happen across the rows. Vice versa, if we want to get the sum for each row, we must specify the axis 1 and we'll get 4 values, 1 for each row. This concludes our introduction to NumPy, where we have covered how to work with arrays, generate random numbers, reshape data, and perform various operations. NumPy is a powerful tool that greatly simplifies working with large datasets in Python. For now, we just worked with dummy data, which seems kind of boring, but we will replace this by real-world data in the upcoming lectures. And this notebook can serve to look up some methods that you might need later.